National Academy of Sciences came out with a study this past December looking at maybe somewhere between 4 and 13% of the driving fleet could be PHEV by 2030. And it's not at all clear when it will become economically viable for the average consumer to partake in that. EPRI says it could already be, depending on how you bookkeep things. And other people say you have to have $10 a gallon gasoline or more before even the smallest battery in a vehicle makes sense. All of these problems, all of these analyses really focus on the battery technology. What kind of cost point do we need? Why is it holding us back? Are two obvious questions. And so that's one of the things I want to probe at right now. And I'll talk a little bit about materials for fuel cells as well, since we had some interesting discourse on that over lunch. So what about lithium-ion batteries? So performance. Performance is largely there. Even if you have a very small pack, and many of, for example, the ones you're driving here, around 5 or 6 kilowatt hours. It's not particularly large, but it's designed to give very high bursts of power and to be able to absorb very high bursts of power, and it works okay. Ought to work for many years, through thousands or at least up to around 1,000 cycles if it's a good battery chemistry that's been designed properly. So that's okay. Technical challenges might be end-of-life use and recycling and safety. We have to figure out what to do with these when we're done with them. They are not particularly hazardous in their constituents. However, we might be able to do something good with them. And also, there are inherent safety issues that we have not gotten around, right? Those are the bottom 2 points. But cost is really what I want to focus on. And it's not really the materials. These cells really are complicated. This is a cutaway of a typical lithium-ion cell, okay? And this particular one is a cylindrical wound bobbin cell style, and the ones that we see going into the vehicles now are either prismatic pouch or prismatic can systems. They're identical to this, except they're kind of squished. So this is sort of an archetypical representation. We have basically some functional powder, some anode and cathode powder that's bulk fabricated, not too expensive, and it's roll casted on double-sided onto very inexpensive foils, copper or aluminum foils. It's got a polymeric separator between those two, and it's backfilled with an organic solvent-based electrolyte, which is sort of the source of a lot of the safety issues. The organic electrolyte will decompose. It contains both organics and oxygen, and it will combust. And it's wrapped really tightly, stuck in this metallic can, vacuumed, evacuated, and then you have to backfill it with the electrolyte. Then you have to have a fully hermetic seal with a carefully engineered venting valve in the event that there is gas buildup on the inside of the cell. And that's just the cell. And then you got to put the cells in series in parallel. Oh, by the way, if you put them in series, they have to be very, very well matched to each other, and they have to maintain that match over many, many charge-discharge cycles. It's far too expensive to have a load leveler or a massive array of switches to take these cells individually on and offline unless you have very large cells, which becomes thermally very difficult to handle in your system. Then you've got all of these other constituents in a pack. And I'm not saying these are centralized necessarily, depending on how your vehicle is designed, but you have to carry these other things, balance of system items. And this is just a cell level, and I'm not going to, of course, go through any of these individual line items, but this is a list of the stuff that's in the batteries. And if you look at the cost of all the stuff, this is for an 8.8 amp hour sort of made-up pouch cell that I have sort of done cost modeling on for various materials and electrode thicknesses and performance parameters. And you see that by far the most expensive aspect of this is the production cost. Depreciation, factory label. Everything else is essentially already at its commodity level, right? So we're not going to change the cost of batteries by getting cheaper or better materials. You can have free anode and cathode functional materials, free, and you're still at a relatively high cost point. This puts us at, this is sort of an average assumption for a good automotive battery, somewhere between $300 and $400 per kilowatt hour. If we're more optimistic, and we make thicker electrodes. So electrode thickness is also very important. We have to use very thin electrodes because the electrolyte that we have has relatively limited lithium-ion conductivity, right? Because that conductivity is limited, it's an order of magnitude worse than even what you would find in an aqueous electrolyte battery, like a lead-acid battery. It's so much worse that in order to be able to handle, or in order to avoid the potential of the lithium becoming lost or not being able to make it across the battery, you have to make every region very thin to accommodate that. And the more power you put per unit mass of battery, the thinner you have to be. So a hybrid vehicle has very, very high power to mass ratio needs. So thinner electrodes, less active material per unit mass cell, higher cost, right? Plug-in, you can get away with a bit more thicker electrode, the cost can go down. And again, about $400 per kilowatt hour is a very optimistic number 5 years down the road if you think that you are going to be able to do some serious mass production. And again, of that money, the materials aspect of it ends right about here at about $100 or so per kilowatt hour. So most of this price is the difficulty in scaling, in production, in yield issues, all of those things. Here's someone else's numbers. This is a very good master's thesis from Duke, a guy by the name of David Anderson. It's available online and recommended if you're curious about another. And he really takes sort of some learning curve theory and some techno-economic analysis, does not go deeply into battery technology. He's not an engineer. He's at the business school. But it is, it's sort of a reality check. I believe that we're somewhere between this blue line and this green line as far as cost at a pack level in dollars per kilowatt hour as a function of year. And I can imagine that we're not going to reach the PHEV 10 goal, cost goal for whatever it's worth set by the United States Department of Energy, which is about $500 per kilowatt hour. They have this happening if you sort of stay in the range where I think is plausible, somewhere between 2018 and 2022. It's a ways off. And this red curve is the wacky, everything goes great. We have free labor in China. And you know, there's no trade tariff on anything, and all the rare earth metals are free, right? So yeah, I mean, there's a lot of stuff like this that make it very difficult to imagine getting down to this point, but there are some scenarios. And this is sort of the more rosy picture that some people who want to promote batteries might adopt, right? And speaking of that, the other thing you want to consider are the metrics of cost that people use when they describe what their batteries are really all about. The makers, they'll use a nameplate capacity. If I make this cell, it will hold, if I go all the way 100% state of charge and fully discharge it, that's the nameplate capacity. And they'll quote that value in dollars per kilowatt hour, nameplate at a cell level or at a pack level. And that is basically not considering what actually is used in driving the car. Now, because of all the systems level constraints associated with battery packs, where you put many of them in series and you have to stay, you're not positive exactly what your state of charge is, and you don't want to do too much degradation on the pack. At a pack level, we end up using about half of that capacity. We keep the state of charge swing moderate, right? So the dollars per kilowatt hour usable at cell and pack level is double that up here, right? And if you even want to be more harsh, you say, well, by the end of life, you define what end of life is. People typically say the end of life of a lithium-ion battery pack or any battery pack is when it has 80% of its initial capacity. So it's dollars per kilowatt hour usable at end of life at a pack level. So National Academy of Sciences also had this study I mentioned already in December. And if you look at that number, even with optimistic assumptions, it's well over $1,000 a kilowatt hour. And there's no near-term way to get that down, in my mind, looking at the way that these materials develop and evolve. So difficult, very difficult. And that is, let's put this into perspective. If you want to go roughly a mile driven takes roughly 250 watt hours, give or take. And so if you want to have a 10-mile range vehicle, you have to carry a 5 or 6 kilowatt hour battery pack. It's a lot of money. It adds up.